Just when scientists thought they had uncovered all the universe's surprises, the James Webb Telescope revealed something truly unexpected: gigantic, fluffy exoplanets that resemble cosmic cotton candy. While their nickname might sound whimsical, these planets present a serious scientific puzzle. Their incredibly low density makes them appear far too light for their massive size, defying our current understanding of planetary formation. In theory, the formation of gas giants like Jupiter follows a clear process. They begin as solid cores with at least 10 times the mass of Earth, accumulating their thick gas envelopes early in their system's development. The gravitational pull of the growing planet ensures it retains its atmosphere, even against the powerful stellar winds of its host star. At least, that's how it's supposed to work. But these newly discovered exoplanets challenge that framework entirely, forcing scientists to rethink what they thought they knew about how planets take shape. That's a theory at least, but when we look at real discoveries in space, we find exoplanets that completely defy expectations, challenging our current models of planetary formation. One of the most puzzling cases appeared on the star charts in 2017. Around 212 light-years from Earth lies WST-107b, a gas giant unlike any other. This alien world completes an orbit around its star in less than 6 days. Initial observations suggested it was similar in size to Jupiter, but deeper analysis over the following years revealed something astonishing. Scientists used a radial velocity method, tracking the minute wobbles of its host star caused by the planet's gravitational pull, to calculate WST-107b's mass. The results were shocking. Despite being as large as Jupiter, this exoplanet weighs only about 30 Earth masses, meaning it is just 10% of Jupiter's mass. This discovery raises a massive question: how can a planet so big be so light? It's a cosmic mystery that's forcing astronomers to rethink everything they know about gas giant formation. Based on these findings, scientists ran model calculations and determined that WST-107b's solid core could be no more than 4 Earth masses. This means the planet is extraordinarily fluffy, with an incredibly low density resembling cotton candy. But that raises an even bigger mystery: how did such a low-density planet even form? And more importantly, how has it managed to hold onto its massive gas envelope without losing it to space? This question becomes even more perplexing when considering WST-107b's close proximity to its star. Being so near, intense stellar radiation should have stripped away much of its atmosphere, yet somehow, this cosmic anomaly has defied expectations. Astronomers quickly realized that this cotton candy planet was an extreme outlier, an object that completely breaks a conventional understanding of how planetary mass and size relate. But if researchers had already been aware of the Kepler-51 system, they would have realized that these so-called absolute outsiders aren't as rare as they once thought. Located 2,600 light-years away in the constellation Cygnus, Kepler-51 is a sun-like star that hosts not one, not two, but 3 of these strangely low-density planets. Faced with an even bigger cosmic puzzle, a team of researchers led by Jessica Libby-Roberts of Pennsylvania State University decided to take a closer look using the powerful James Webb Telescope. They set out to unravel the mystery of how these bizarre, fluffy worlds could exist, and what they might reveal about planetary formation in the universe. But when scientists aimed the James Webb Telescope at Kepler-51 before the expected transit, they were caught off guard by an unexpected twist. The planet's shadow appeared far earlier than predicted. Instead of witnessing the start of the transit, they had unknowingly tuned in just in time to see its conclusion. The numbers told a shocking story. Kepler-51d had begun its journey across the star a full 2 hours ahead of schedule. Normally, minor deviations in transit timing, just a few minutes, can be explained by gravitational influences or orbital shifts. But a discrepancy of this magnitude was something entirely different. So, what could have caused this planetary misalignment? That was the million-dollar question. Co-first author Kento Masuda from the University of Osaka admitted that the early arrival of Kepler-51d left him, and his team completely baffled. No matter how they adjusted their models of the three-planet system, nothing could account for such a drastic shift. One thing was certain: this wasn't a mistake by the James Webb Telescope. The data was solid. Something strange was going on in the Kepler-51 system, and unraveling this mystery could mean rethinking what we know about planetary orbits and interactions. The mystery deepened when the early transit wasn't just a one-time anomaly. It was confirmed by the Hubble Space Telescope and multiple Earth-based observatories. The evidence was undeniable, but what could possibly explain this cosmic curveball? The answer lay in an expanded model of the system, one that included a 4th, previously unknown planet. This elusive world, now dubbed Kepler-51e, likely orbits farther out on a more inclined trajectory. Because of this tilt, it never transits directly in front of its star from our viewpoint on Earth, but its gravitational influence is enough to disrupt the motion of its neighboring planets. Further analysis suggested that Kepler-51e is another gas giant, similar in mass to its 3 siblings. This means the Kepler-51 system isn't just home to three bafflingly lightweight candelfloss-like planets. It's actually a quartet of cosmic oddities. Even with this new addition, though, the planets are still far too fluffy to fit into our conventional models of planet formation. Adding to the intrigue, most of these cotton candy worlds tend to be solitary within their systems, yet here we have four in one place. Could there be even more hidden planets beyond Kepler-51e? Scientists are now eagerly turning to the James Webb Telescope's high-resolution spectrograph, hoping to peel back more layers of this planetary enigma and finally uncover what makes these puffed-up worlds so unique. The Kepler-51 system isn't the only planetary arrangement leaving scientists scratching their heads. While its cotton candy planets challenge density expectations, another system, WST-132, is turning planetary formation theories upside down with its unexpected diversity. Located about 400 light-years away, WST-132 boasts a lineup that looks like a cosmic mashup, a super-Earth, a hot Jupiter, and a massive ice giant, all orbiting the same star. This combination is unusual because hot Jupiters, gas giants that orbit extremely close to their stars, are typically lone wanderers. Their formation model suggests they should have formed farther out in their systems and only later migrated inward, bulldozing any smaller planets along the way. Yet here, a hot Jupiter coexists with two very different planetary types. How did this happen? Did this gas giant move inward without disrupting its neighbors, or did these planets form under conditions that defy our current understanding? These questions push astronomers to rethink planet evolution. WST-132 proves that nature doesn't always follow the rules we expect, reminding us that the universe still holds plenty of surprises. The WST-132 system continues to baffle scientists with its unexpected planetary lineup. The super-Earth orbit even closer to the star than the hot Jupiter, completing a full lap in just over a day, while the gas giant takes about 7 days. But the true outlier is the ice giant, lingering much farther out with an orbit stretching over 1,800 days. Adding to the intrigue, the star's light curve hints at another hidden companion, possibly a brown dwarf. These mysterious objects sit between planets and stars, blurring the line between the two. However, the presence of a hot Jupiter in this system challenges existing migration theories. Normally, such gas giants form farther out and drift inward, disrupting smaller planets in the process. Yet here, the super-Earth remains intact, and the ice giant's orbit appears undisturbed. This suggests the hot Jupiter's migration was unusually smooth, avoiding the chaotic gravitational interactions expected in such a system. But exactly how this happened remains a mystery. Certainly, below is a continuation of your article, expanded to reach approximately 1,800 words while maintaining the original style and scientific depth. The mystery of ultralight exoplanets deepens. The discovery of these bizarre cotton candy-like exoplanets has sent shockwaves through the field of planetary science. Their existence forces astronomers to reconsider long-held assumptions about how planets form and evolve. If gas giants can exist with such low densities, what other surprises might the universe be hiding? One leading theory suggests that these super-puff planets might have formed much farther from their host stars before migrating inward. In the colder outer regions of a planetary system, gas can accumulate more slowly, potentially leading to a fluffier structure. However, this still doesn't fully explain how these planets retain their massive atmospheres despite being so close to their stars now. Another possibility is that these worlds are undergoing rapid atmospheric escape, losing their outer layers due to intense stellar radiation. If that's the case, we might be catching them in a fleeting stage of their evolution, like cosmic soap bubbles on the verge of popping. Yet, if they were losing gas at such a dramatic rate, we should see evidence of massive outflows, something that hasn't been consistently observed. The role of magnetic fields and unusual chemistry. Some researchers speculate that strong magnetic field could be shielding these planets from their stars' harsh winds, preventing atmospheric loss. Alternatively, their atmospheres might be composed of unusual molecules that behave differently under extreme heat and radiation, making them more resilient than expected. The James Webb Space Telescope, JWST, is now playing a crucial role in solving this mystery. By analyzing the chemical composition of these planets' atmospheres, scientists hope to find clues about their origins. For instance, if JWST detects an abundance of heavy molecules like carbon dioxide or methane, it could suggest that these planets formed in a unique environment where such gases were dominant. Kepler-51, a system defying all expectations. The Kepler-51 system remains one of the most perplexing discoveries in exoplanet research. With 3, and possibly 4, ultra-low-density planets, it challenges the idea that such worlds should be rare. If these planets formed under special conditions, why are there so many in one system? One hypothesis is that Kepler-51 star was surrounded by an unusually extended protoplanetary disk, a vast, diffuse cloud of gas and dust, during its early formation. In such an environment, planets might have accumulated large atmospheres without developing massive cores, leading to their current fluffy states. Another intriguing possibility is that these planets were once much larger but have since lost significant amounts of gas, leaving behind their puffy remnants. If true, this would imply that we're seeing the ghost of former gas giants, their cores long since stripped of much of their original mass. WST-132, a cosmic oddity among hot Jupiters. While Kepler-51's cotton candy planets baffle scientists with their low density, the WST-132 system presents a different kind of puzzle. The presence of a hot Jupiter alongside a super-Earth and an ice giant defies standard planetary formation models. Hot Jupiters are usually thought to form far from their stars and then migrate inward, a process that should disrupt smaller planets in their path. Yet in WST-132, the super-Earth remains unscathed, orbiting even closer to the star than the gas giant. How did this happen? One explanation is that the hot Jupiter's migration was unusually gentle, perhaps due to interactions with a protoplanetary disk rather than violent gravitational encounters. Alternatively, the super-Earth might have formed after the hot Jupiter settled into its current orbit, avoiding catastrophic collisions. The possible presence of a brown dwarf, a failed star too small to sustain nuclear fusion, adds another layer of intrigue. If confirmed, this object could have played a key role in shaping the system's architecture, its gravity subtly influencing the orbits of the inner planets. The future of exoplanet research. As astronomers continue to study these strange worlds, new missions and telescopes promise even more groundbreaking discoveries. The European Space Agency's Plato mission, set to launch in 2026, will focus on finding Earth-like planets around Sun-like stars, but it may also uncover more of these enigmatic, fluffy worlds. Meanwhile, ground-based observatories like the extremely large telescope ELT will provide unprecedented detail on exoplanet atmospheres, helping scientists determine whether these planets are truly losing their gas or if some unknown mechanism is keeping them intact. Could there be more cotton candy planets out there? Given how recently these low-density exoplanets were discovered, it's likely that many more exist, hidden in the vast datasets of past and ongoing surveys. Future observations might reveal that these worlds are not as rare as we once thought. Perhaps they've simply been overlooked because their unusual properties made them hard to detect. If that's the case, our understanding of planetary formation may need a major overhaul. Current models are based on our own solar system, where gas giants like Jupiter and Saturn have much higher densities. But if fluffy, low-mass giants are common elsewhere, we may need entirely new theories to explain them. A cosmic reminder, the universe is full of surprises. The discovery of cotton candy exoplanets, along with systems like WST-132 and Kepler-51, serves as a humbling reminder that the universe is far stranger than we imagined. Just when we think we figured out the rules, nature throws us a curveball, or in this case, a giant, fluffy planet that shouldn't exist. As technology advances, we can expect even more bizarre and wondrous discoveries. Who knows what other planetary oddities are waiting to be found? Perhaps one day, we'll even uncover a world that defies all known physics, forcing us to rewrite the textbooks entirely. Conclusion: the never-ending quest for knowledge. The study of exoplanets is one of the most exciting frontiers in modern astronomy. Every new discovery challenges our assumptions and pushes the boundaries of what we thought possible. From ultralight cotton candy planets to systems where gas giants coexist with super-Earths, the universe continues to surprise us at every turn. As scientists refine their models and gather more data, one thing is certain: the cosmos is far more diverse and mysterious than we ever dreamed. And with powerful tools like the JWST and future telescopes, we're only just beginning to scratch the surface of these cosmic enigmas. So, the next time you look up at the night sky, remember, there are worlds out there unlike anything in our solar system, defying expectations and expanding our understanding of what a planet can be. And who knows, maybe the next big discovery is just around the corner, waiting to astonish us all. If you're enjoying these cosmic puzzles, don't forget to hit that subscribe button and give this video a thumbs up. There's always more space to explore, and you won't want to miss what's next.